Chapter 1: Anatomy of a Style Sheet. Welcome to Chapter 1. This is where CSS stops being history and starts being code. In this chapter, you'll learn the anatomy of a style sheet, how to write and format rules, what vendor prefixes are and why they exist, how to leave comments, and most importantly, every single way to get CSS into the browser. From the classic link tag to inline styles, from @import to how files travel over the network, we'll cover the plumbing that makes styles appear on screen. By the end of this chapter, you'll not only write valid CSS, you'll understand exactly how the browser reads, loads, and applies it. Let's get started. Section 1.1: Anatomy of a Style Sheet. What exactly is a style sheet? At its most fundamental level, a style sheet is nothing more than a plain text file, just like a .txt file, but saved with a .css extension. It contains characters, letters, numbers, symbols, and spaces, all encoded in UTF-8, which is the standard character encoding for the web. There's no magic format, no compiled binary. You can open a CSS file in Notepad, VS Code, or any editor, and you will see exactly what you wrote. This simplicity is deliberate. CSS was designed to be human-readable, easy to write, and easy to debug. The file extension .css signals to the browser and to your tools that this file contains cascading style sheet rules. When a browser downloads this file, it parses the text and converts it into a set of declarations that will control the visual rendering of the page. A crucial mental shift. A style sheet is not a program. In a language like JavaScript, you write step-by-step instructions that tell the computer what to do. Loop over this array, check this condition, update that element. CSS works completely differently. A style sheet is a collection of style declarations, a set of descriptions of how elements should look. There are no loops, no conditional logic in the traditional sense, no ability to store or manipulate data during execution. You simply declare, I want all heading level 1 elements to be navy blue, and the browser's rendering engine takes care of the rest. This is called a declarative language. You describe the desired outcome, and the browser figures out how to achieve it. This is why CSS is often easier to learn at first. You don't have to think about control flow, just about what looks right. Every web page you visit is styled by not one, but potentially 3 separate style sheets. The first is the user agent style sheet, which is built into the browser itself. This is why, without any CSS of your own, headings look bigger than paragraphs, links are blue and underlined, and lists have bullet points. The second is the user style sheet, which is less common but still exists. It allows a user to define their own personal styles, such as a minimum font size or high contrast colors, often for accessibility reasons. The third is the author style sheet, that's you. You create these rules to override the browser defaults and achieve your own design. The Cascade, which we'll dive into in Chapter 4, decides how these 3 origins combine and which rules win when there's a conflict. But the important concept right now is that a style sheet is not an island. It lives in a system where multiple sources of styles flow together. Think of a style sheet as a recipe book and the browser as the chef. The recipe doesn't cook the meal. It just describes what ingredients to use and what steps to follow. In the same way, a CSS file doesn't draw pixels on the screen. It describes how elements should be colored, spaced, and sized. The browser reads that description and uses its layout engine, the rendering engine, to calculate the exact position and appearance of every box on the page. This separation is powerful. The same recipe, the same CSS, can be used by different chefs, different browsers, and still produce a delicious result, a consistent website. That's why standards matter. As long as all browsers agree on what margin left, 2M, means the output will be predictable. A style sheet is fundamentally a list of rules. Each rule consists of a selector and a declaration block containing one or more property value pairs. These rules can be added in any order, and they don't execute sequentially like a script. Instead, they all exist at once, and the browser collects them all, figures out which ones apply to which elements, and then resolves any conflicts using the cascade. That means you can spread your styles across multiple rules, across multiple files, and even across the 3 origins. The style sheet is a declarative collection. It's the cascade that determines the final appearance. Understanding this, that you're writing a pool of possibilities, not a linear program, is key to writing predictable, maintainable CSS. So to sum up the anatomy, a style sheet is a plain text.css file encoded in UTF-8 containing a collection of CSS rules. It's not a program, but a declarative specification of how elements should look. It's one of up to 3 style sheet origins that the browser combines to render the final page. And it works like a recipe, describing the desired result while the browser does the heavy lifting. This foundation, simple as it is, underpins everything you'll learn in this course. Next, we zoom in on the smallest building block inside any style sheet, the CSS rule itself. Let's dissect exactly how rules are written. Section 1.2, How CSS Rules Are Written. Let's zoom in on the most fundamental building block of any style sheet, the CSS rule. A rule connects a selector to a declaration block. The selector, in this case, H1, tells the browser which element or elements you want to style. The declaration block, wrapped in curly braces, contains one or more declarations. Each declaration is a property followed by a colon and a value, terminated by a semicolon. So color, navy, sets the text color to navy blue, and font size, 2 rem, makes the text twice the root font size. You can put as many declarations inside a single rule as you like. When the browser parses this rule, it finds every H1 element in the document and applies all of these declarations simultaneously. That's it. Selector, curly braces, property, colon, value, semicolon. That's the core pattern you will write thousands of times. Punctuation is critical inside a declaration block. The colon separates a property from its value, and the semicolon separates one declaration from the next. If you forget a semicolon, the browser will read everything up to the next semicolon as part of the previous value, which almost certainly produces an invalid value. In the example on screen, the browser tries to interpret dark green font size. 1.5 rem as a single color value, fails, and silently ignores that entire declaration. Then it reaches font size, 1.5 rem, but it has already dropped the faulty line, so the font size declaration is lost too. This is why a missing semicolon can cause 2 declarations to disappear at once. The fix is simple. Always end every declaration with a semicolon, even the last one. It prevents errors when you add more properties later. CSS is remarkably forgiving when it encounters errors, but in a very specific way. If the browser hits a declaration it doesn't understand because the property name is misspelled or the value is malformed or the entire syntax is garbled, it simply skips that one declaration and moves on to the next. It does not crash. It does not throw an error to the user. The rest of the rule and the rest of the style sheet continues to work. This is called error handling, and it's a deliberate design choice to keep the web resilient. However, if the selector is invalid, for example, a class name starting with a digit or double dots, then the browser discards the entire rule block because it can't reliably know which elements were meant to be targeted. So, a broken declaration? The rule survives. A broken selector? The whole rule is thrown out. This behavior is your safety net, but it also means you need to check your syntax carefully. The browser won't always tell you something went wrong. Now let's talk about whitespace inside rules. In most places, CSS doesn't care about spaces, tabs, or line breaks. You can write a rule on one line or spread it across 10. The browser will treat both identically. The style on the left is perfectly valid. It's just hard to read. The style on the right is the same rule formatted for humans. However, whitespace is not always optional. When a value consists of multiple parts, like 2px solid red for a border, the parts must be separated by at least one space. If you remove those spaces, the browser sees 2p solid red and has no idea what that means, so it ignores the declaration. The same applies to font shorthand, grid definitions, and function arguments like RGB, 255, 0, 0. As a rule of thumb, always put a space after the colon, and always separate multi-keyword values with spaces. Your eyes and the browser will thank you. So, formatting conventions. They don't change how the page looks, but they radically change how easy your code is to read, debug, and maintain. Here's a widely adopted style you'll see in this course. Put the opening curly brace on the same line as the selector after a space. Place each declaration on its own indented line. Use a space after the colon. Always end with a semicolon even on the last declaration. Leave an empty line between rules to visually separate them. This isn't the only way. Some developers prefer the opening brace on its own line, or tabs instead of spaces. The key is consistency. Pick a style and stick to it. Your code will be scanned by other developers, and by your future self who has to fix a bug at 11 p.m. Good formatting is a gift you give yourself. To recap, a CSS rule is a selector plus a declaration block. Inside that block, declarations pair properties with values, separated by a colon and terminated by a semicolon. The browser ignores what it doesn't understand, so invalid declarations are skipped while valid ones survive. Whitespace is mostly free, but required between parts of a multi-keyword value. And while the browser doesn't care about formatting, you should, because code is read far more often than it is written. In the next section, we'll explore why you sometimes see strange dashes like WebKit or Maz in front of properties, and the story of vendor prefixes. Section 1.3, Browser Experiments, the prefix story. If you've ever looked at an older style sheet, or even some modern ones, you may have seen properties that start with strange hyphens, WebKit-, Maz-, MS-, O-. These are called vendor prefixes. They look like a secret code, but their story is surprisingly straightforward. In the late 2000s, as CSS3 modules were being drafted, browser vendors wanted to ship new features to developers as soon as possible, but those features weren't yet standardized. The specifications could still change. So each browser wrapped its experimental implementation in a unique prefix, a kind of namespace that signaled, "This is our early version. It might behave differently or change later." This allowed developers to test the future of CSS today without breaking the web when the spec eventually changed. Each browser engine had its own prefix. WebKit for Safari and later Chrome, Maz for Firefox, MS for Internet Explorer, and O for Opera. When a browser wanted to try out a new property like border radius before it was fully standardized, it would implement it under its prefix. So developers would write the same property multiple times, once with each prefix, and then the unprefixed standard version at the bottom. The browser would ignore the prefixes it didn't understand and apply its own. When the spec stabilized and all browsers agreed on the standard name, developers could remove the prefixes, but many didn't, and those old prefix lines lingered in Stylesheets for years. This was the birth of prefix debt. But then a deeper problem emerged. During the mobile web explosion, Safari and Chrome, both using the WebKit engine, dominated smartphones and tablets. Many developers, pressed for time or unaware of best practices, only wrote WebKit prefix properties and skipped the others. They assumed the other browsers would just use the unprefixed standard, but often the standard hadn't shipped yet. This created a web that was effectively broken in Firefox and Opera on mobile. The situation became so severe that Mozilla announced it would start honoring certain WebKit prefixed properties in Firefox, just to make the web work. The prefixes had escaped the lab. Instead of being a temporary experiment, WebKit became a de facto requirement. This is the nightmare scenario that vendor prefixes were supposed to prevent. Thankfully, browser vendors learned from this. The modern approach is much healthier. Instead of shipping experimental features with prefixes by default, browsers now hide new features behind feature flags, settings that developers and early adopters can manually enable to test. This allows real-world experimentation without polluting the global web. When a feature is stable and the specification is solid, the browser ships it unprefixed, usually without a prefix transition period at all. Alongside this, CSS introduced its supports, a way to test whether the browser supports a given property and value combination before applying styles. So instead of writing 4 prefixes and hoping, you can write it supports, display, grid, and provide a fallback for browsers that don't support it. Feature detection has replaced prefix guessing. In production today, very few developers write vendor prefixes manually. Instead, we use tools like Auto-Prefixer, a post-CSS plugin that reads your style sheet, checks browser usage data from Canius, and automatically inserts only the prefixes that are still needed for your target browser list. You configure it once, typically with a browser's list string like last 2 versions, greater than 0.5% market share, and not dead. Then every time you build your CSS, Auto-Prefixer adds the minimum necessary prefixes and nothing more. This means you write clean, standard CSS, display, flex, and the tool outputs the backward-compatible version. This is the standard practice on any modern project. You focus on the future, the tool handles the past. In this course, you'll occasionally see us write vendor prefix properties manually, especially when demonstrating a feature that is still behind a prefix in some browsers, like WebKit Backdrop Filter. We do this for transparency so you can see exactly what the browser is reading. But for your own projects, the rule is simple. Write the unprefixed standard, let Auto-Prefixer handle the rest. Understanding the prefix story is important because it explains why some codebases still have them, and why the web had a messy adolescence. But now you know the modern way, feature flags for experimentation at supports for safe detection, and Auto-Prefixer for production-ready compatibility. That's the prefix story. Next, let's talk about whitespace, those invisible characters that can make or break your styles. Section 1.4. Space, gaps, and invisible characters. Let's talk about something you can't see but absolutely have to understand: whitespace. In CSS, whitespace refers to spaces, tabs, and line breaks. For the most part, the CSS parser treats all of these the same, as a separation between tokens. Whether you put 1 space or 20 spaces between the property name color, followed by a colon and the value navy, the browser sees exactly the same thing. You can break a rule across dozens of lines, or cram it onto a single line. The rendering will be identical. This freedom is what makes CSS so flexible to write. But there are specific places where whitespace suddenly becomes critical, and getting it wrong will break your styles. So let's map out exactly where whitespace is harmless. In CSS, punctuation like curly braces, colons, semicolons, and commas are hard stops. The parser can identify them without needing any whitespace around them. So a rule written as h1 left curly brace color colon navy semicolon right curly brace is perfectly valid, even though there's no space after the colon. The tokenizer in the browser's CSS engine scans the characters and knows that an opening curly brace starts a block, a closing curly brace ends it, a colon separates a property from a value, and a semicolon ends a declaration. You can add spaces to make it readable, or remove them to save bytes. This is why minification tools can strip all unnecessary whitespace without breaking anything. The only requirement is that you don't join words together that would form a different token. That example, h1 left curly brace color colon navy semicolon right curly brace, works because the parser can still distinguish the opening curly brace from the selector, h1. However, there are places where spaces are not optional, they are mandatory. Let's see those. Now the critical part. Whitespace is not always optional. First, inside quoted strings, like a font family name in double quotes such as Times New Roman, every space is a literal character. If you remove them, you're asking for a different font entirely. Second, when a CSS value is made up of multiple keywords, like the border value 2px solid red, the spaces between them are mandatory. They tell the parser that 2px, solid, and red are 3 separate components. If you write 2p solid red as a single word, the parser sees a single unknown token and discards the entire declaration. Third, within functions like RGB parentheses, commas separate the arguments and spaces around those commas are recommended for readability but not strictly required. However, if you omit the comma entirely and rely on a space, the parser might merge the numbers into one value. The rule: always put spaces between multi-keyword values, and always use commas inside functions. This next part is actually an HTML behavior, but it trips up CSS beginners, so we'll address it head-on. In HTML, multiple consecutive whitespace characters inside text content collapse into a single space when rendered. That's why 5 spaces between words look like one on the page, unless you use a pre-element or set the CSS property whitespace to pre. This collapsing is not a CSS property. It's part of HTML's text layout rules. CSS can control it via the whitespace property, which we'll explore in the text properties chapter. For now, just know that the spaces you type inside your CSS declarations and selectors behave differently from the spaces inside your HTML content. The spaces in your CSS rules are token separators. The spaces in your HTML text are subject to collapsing. Don't confuse the two. So the golden rule with whitespace is, when you're writing code, use generous whitespace to make your style sheets readable. Indent your declarations, put spaces after colons, separate rules with blank lines. Your future self and anyone else reading your code will thank you. When you deploy to production, use a build tool to minify that CSS. Strip all unnecessary whitespace, remove comments, and shorten values where possible. This reduces file size and improves load times without changing how anything looks. You don't have to choose between readability and performance. You get both. Write clean, formatted CSS in development. Let your tooling compress it for the web. To summarize, whitespace in CSS is largely invisible to the parser, but there are precise situations where it becomes essential. Always separate multi-keyword values with spaces. Never remove spaces inside quoted strings. Understand that whitespace collapsing is an HTML text rendering behavior, not a CSS syntax rule. And adopt a formatting style that makes your code a pleasure to read, because you'll spend far more time reading it than writing it. Next, we'll cover another invisible but vital part of any style sheet: comments. How to leave notes for yourself and others without breaking anything. Section 1.5. Leaving notes in your style sheet. CSS is a language meant for both browsers and humans. The browser needs clean, valid rules to render a page. But you and any other developer who touches your code need something else: context. That's where comments come in. A CSS comment is a piece of text wrapped inside /* and */. Everything between those markers is completely ignored by the browser. It doesn't affect rendering. It doesn't change the cascade. It's simply invisible to the CSS engine. Comments are a communication channel from you to your future self, and from you to your teammates. They explain why something is the way it is, warn of gotchas, or just help you navigate a large file. In this section, we'll cover the syntax, rules, best practices, and a few surprising things about CSS comments. The syntax is straightforward. / starts a comment, and * ends it. There's no dedicated single-line comment syntax in CSS, like double slash in JavaScript. But you can absolutely write a comment that fits on one line, and that's the most common usage. For longer notes, you can spread the comment across multiple lines. The browser will ignore everything from the opening / to the closing */, no matter how many lines are in between. This is also extremely useful for temporarily disabling a rule or a declaration. If you suspect a property is causing a problem, you can comment it out rather than deleting it, test the page, and easily restore it later. Comments are the ultimate non-destructive editing tool. There's one important limitation. CSS comments cannot be nested. If you try to put one comment inside another, the first * the parser encounters will close the entire comment, regardless of how many / markers came before. The result is that some of your intended comment text gets exposed as raw CSS, which will almost certainly cause a parse error. This is a common gotcha when you're trying to comment out a large block of code that already contains comments. The workaround? Either remove or uncomment the inner comments before wrapping the block, or use a different marker like /*, 3 dashes, */ to visually separate sections without trying to nest. Most code editors will highlight this issue for you by coloring the comment oddly, so keep an eye out. Good comments explain the why, not the what. The CSS itself already tells you the what. Color red : is self-explanatory. But why is it red? Why did the developer use a very specific selector? Why is this value hard-coded instead of using a custom property? That's what comments are for. Use them to divide your style sheet into logical sections with visual headers, to mark things that need future attention with to-do or fixum tags, and to explain any non-obvious decisions like a browser-specific hack, a magic number, or a temporary workaround. When you come back to this code 6 months later, or when a new team member joins, those comments are the difference between immediate understanding and hours of detective work. Comment like you're writing a letter to a future colleague who's having a bad day. Comments are visible in the browser's DevTools if you look at the raw source of the style sheet, but they never appear in the computed styles or affect any element. They are purely source-level artifacts. This means they do add to the file size. Every character in a comment is a byte that must be downloaded. For most development work, this is negligible. But for production, it's standard practice to strip comments out during the build process, along with all other unnecessary whitespace. Minification tools do this automatically, so you can comment as liberally as you want during development, and your production CSS will be lean and clean. The comments serve their purpose, they help the humans, and then they gracefully disappear before reaching the end user. Comments are your invisible allies. They cost nothing in rendering, and they provide immense value during development and maintenance. The rules are simple. Everything between /* and */ is ignored. Use them wisely to explain, organize, and protect your code. In the next section, we'll shift focus back to HTML, specifically the document object model, the living tree that CSS actually targets. You'll learn to see the page the way your style sheet sees it. Section 1.6. The HTML skeleton, what CSS sees. So far, we've been treating HTML as the raw text you write in a file. But when the browser loads your page, it doesn't keep that text as a flat string. It parses the HTML and builds a living, tree-like structure in memory called the document object model, the DOM. The DOM represents every element, every attribute, and every piece of text as a node in a hierarchy. This is what CSS actually targets. The browser doesn't match selectors against your original HTML file. It matches them against the DOM. Understanding this distinction is critical because it explains why CSS can style dynamically added elements, why selectors follow parent-child relationships, and why the Cascade sometimes behaves unexpectedly. Let's walk through exactly what the DOM is and how CSS sees it. The DOM is built by the browser's HTML parser. When the parser encounters an opening tag, for example, a div tag, it creates an element node. When it encounters text, it creates a text node. When it encounters a closing tag, it knows the node is finished and returns to the parent. The result is a precise tree of parent-child-sibling relationships. The DOM is not just a copy of your HTML. It's a live data structure. If your HTML is malformed, the browser will fix it in the DOM, adding missing closing tags or rearranging elements according to the HTML specification. That's why the DOM you see in DevTools might look slightly different from your raw source. CSS works exclusively with this cleaned-up, structured DOM. It never sees your original file. The DOM is not static, can be modified in real time by JavaScript. And because CSS matches against the live DOM, any new element added, whether from a user interaction, an API response, or a framework update, is instantly styled by the existing CSS rules. The selectors are reevaluated continuously as the DOM changes. This is the foundation of all dynamic web interfaces. When you write a selector like card h2, that is, a class named card followed by an h2 element, you are not saying style any h2 element that was inside a card at page load. You are saying style every h2 element that is a descendant of an element with the class card, now and forever, whenever the DOM matches that pattern. It's a declarative relationship that the browser maintains for you. Understand this, and you'll stop fighting, why isn't my new element styled? It always is because the rule is live. The best way to internalize this is to use the browser's developer tools. Open DevTools, click the arrow icon, and hover over any element on the page. The DOM tree will expand to show you exactly where that element lives in the hierarchy. The Styles panel tells you every rule that matches and why. You can even edit the DOM directly, change tag names, add classes, wrap elements, and watch CSS instantly update. This is the ultimate learning laboratory. Whenever you're unsure why a style is or isn't applied, the first question is, what does the DOM look like right now? Not what your HTML file looks like, not what you intended, but the actual live DOM that the browser is styling. DevTools shows you that truth. Since CSS works with the DOM, the quality of your DOM matters. Semantic HTML, using elements like header, nav, main, section, article, footer, button, input, gives your document structure and meaning. CSS can target these just as easily as div elements, but the benefit goes beyond styling. Screen readers, search engines, and other tools rely on semantics to understand your content. A page built entirely with div elements is a div soup, functional but meaningless. A page built with proper semantic elements is a structured document. CSS works beautifully with both, but your future self and anyone relying on assistive technology will thank you for choosing semantics. Plus, many semantic elements come with useful browser defaults like keyboard accessibility that you would otherwise have to recreate. The DOM is the bridge between your HTML and your CSS. It's a live, structured tree that the browser builds, maintains, and continuously matches your selectors against. Once you start thinking in terms of the DOM, not the raw file, many CSS mysteries dissolve. You understand why dynamically added elements are styled, why the cascade follows parent-child lines, and why using semantic HTML isn't just about good practice. It's about giving your styles a clean, meaningful target. In the next section, we'll explore a fundamental distinction within the DOM, the two different kinds of element boxes, and how CSS treats them very differently. Section 1.7, Two kinds of elements, content versus placeholder. The DOM tree we explored in the last section is filled with many kinds of elements, but from the perspective of CSS, they all fall into two fundamental categories: non-replaced elements and replaced elements. The distinction isn't about what the element means. It's about how the content gets into the box. A non-replaced element like a paragraph or a div acts like a container. Its content, text, other child elements, is placed inside it, and the box grows to hold that content. A replaced element, on the other hand, is a placeholder. The content isn't in the document. It's an external resource, an image file, a video stream, a plugin, or an OS-level form control. The element itself is simply a portal, and the browser replaces the entire box with the external content. This one distinction governs how dimensions, pseudo-elements, and aspect ratios behave. Let's unpack both in detail. Let's look closely at non-replaced elements. Paragraphs, headings, div elements, span elements, lists, and most semantic elements fall into this category. The key property: their content is rendered inside the element's own box. If you put text inside a paragraph, that text becomes part of the element's content area. The element's default dimensions are determined by its content and the width of its containing block, the parent. If you add more text, the box gets taller. If you remove all the content, the box collapses to nothing. But you can override this with CSS. Set a fixed width and height, and the box ignores its content size, potentially overflowing. Because the box and the content are separate layers, CSS can manipulate the box model, padding, borders, margins independently, and it can also insert extra visual content using the double colon before and double colon after pseudo-elements, which we'll cover later. Now contrast that with replaced elements. An IMG element has no text content between its opening and closing tags. It's a void element. The actual visual content is fetched from a URL. The browser downloads the image, decodes it, and then renders it entirely inside the elements box. Crucially, the browser knows the natural dimensions of that image, its intrinsic width and height. If you don't specify any CSS size, the element defaults to those intrinsic dimensions. Set only the width, and the height automatically scales to preserve the aspect ratio. The same principle applies to video, canvas, iframe, and form elements like input, select, and button. These elements are rendered by the operating system or a browser internal subsystem, not by the normal CSS box layout flow. The CSS box model still exists. You can add padding, borders, and margins, but the internal content is entirely opaque to CSS. You can't style the text inside an input element's actual text field with a simple selector that requires special pseudo-elements like the double-colon placeholder pseudo-element. The element is a window to something outside the document. This is one of the most immediate practical consequences of the distinction. You cannot use the double colon before and double colon after pseudo-elements on replaced elements. Why? Because a pseudo-element is like a virtual child element that gets rendered inside the content area. A replaced element doesn't have a content area in the same sense. The entire box is taken over by the external renderer. There's nowhere for a pseudo-element to go. So img double colon before, video double colon after, input double colon before, these will all fail silently. If you need decorative elements around an image or a custom checkbox, you wrap the replaced element in a non-replaced wrapper element and put the pseudo-elements on that. This is a common pattern in UI development, and it's driven entirely by the replaced versus non-replaced divide. This brings us to aspect ratios. A replaced element like an image has an intrinsic aspect ratio, the ratio of its natural width to its natural height. If you set only one dimension, the other adjusts automatically to preserve that ratio. A non-replaced element has no intrinsic aspect ratio. If you set width to 100%, the height is determined solely by its content, which may be 0. This is why empty div elements collapse to 0 height unless you give them a height or content. However, modern CSS now allows you to give any non-replaced element a defined aspect ratio using the aspect ratio property. This makes layout far more flexible. But it's a deliberate addition, not a default. The browser treats the intrinsic aspect ratio of a replaced element as a hard fact. The aspect ratio of a non-replaced element is a suggestion you provide. To summarize, the DOM is filled with two fundamentally different types of elements. Non-replaced elements are containers. Their content is part of the document, and CSS can shape them and inject pseudo-elements freely. Replaced elements are windows to external worlds. Their content is opaque. They bring their own dimensions and aspect ratios, and pseudo-elements can't touch them. Knowing which is which will save you hours of debugging and help you build layouts that behave predictably. In the next section, we'll look at how CSS categorizes elements by their flow behavior, block, and inline, and how the display property can change an element's fundamental nature. Section 1.8 Block, Inline, and the Display Role. In the last section, we divided elements into non-replaced and replaced. That's about where the content comes from. Now we encounter a second, equally fundamental categorization: how an element behaves in the flow of the document. By default, some elements, like headings, paragraphs, and divs, create a block that stretches across the full available width and starts on a new line. Others, like links, spans, and emphasized text, flow within the text like words in a sentence. This behavior is called the display role, and it is the single most important factor in how elements are laid out on a page. Let's explore block and inline elements in detail and see how CSS can override these defaults with the display property. A block-level element behaves like a paragraph in a word processor. It always starts on a new line, even if there's space to its right. By default, it stretches to fill the entire width of its containing block, usually the parent element or the viewport. Its height is determined by its content. A block with a single line of text is only as tall as that line. If you explicitly set a width, the box shrinks, but it still insists on its own line. The next element, even if it's also narrow, will appear below it, not beside it. This is the core stacking behavior of block elements. They create vertical rhythm in a layout. Examples include div, h1 through h6, p, header, footer, section, and the list goes on. When you see a page with distinct horizontal sections, each one is likely a block element. Now let's look at inline elements. An inline element does not start on a new line. It flows within the text, like a word or a punctuation mark. A span, for example, is the generic inline wrapper. If you wrap a few words in a span, those words stay exactly where they are in the sentence. The box created by the inline element is only as wide as its content. You can give it a background color or a border, and those will hug the text tightly. But here's a critical point. Inline elements ignore explicit width and height declarations. The box's dimensions are entirely determined by the content and the line height. Padding and margins work horizontally, but vertical padding and margins on inline elements don't push other lines away in the same way block elements do. They can overlap adjacent lines. Inline elements are designed for typographic styling, not for structural layout. Let's solidify the differences with a side-by-side comparison. Block elements. Start on a new line, take the full available width, respect explicit width and height, and their vertical margins push other blocks away. They can contain other block elements, inline elements, and text. Inline elements flow within text are only as wide as their content, ignore width and height, and their vertical margins don't affect block layout in the same way. They primarily affect line spacing. Inline elements are typically used for text-level semantics and should generally contain only other inline elements and text, not block elements. This isn't just a stylistic choice. It's part of the HTML specification. Nesting a block element inside an inline element can lead to unpredictable layout behavior because the browser may restructure the DOM to correct the error. The display property is the great transformer. With a single declaration, you can make a block element behave like an inline one, or an inline element stack like a block. There's also inline block, which is a hybrid. It flows inline like text, but it respects width and height like a block. And then there's display:"none, which removes the element and all of its children from the rendered layout entirely. The element still exists in the DOM. It's just not painted on screen and doesn't take up any space. This is different from visibility:"hidden, which hides the element but preserves its space. We'll dive deep into all the display values in Chapter 6, but for now, the key insight is the display role is not fixed. HTML provides a default, but CSS can override it at any time. This flexibility is what makes modern layouts possible. To summarize, every element has a default display role, block, or inline that dictates how it behaves in the document flow. Block elements stack vertically and stretch to fill the container. Inline elements flow horizontally and hug their content. The display property can override these defaults, making any element behave in a completely different way. Understanding this is essential because every layout decision you make builds on top of this foundation. In the next section, we'll pull back and look at the three mechanisms that deliver CSS rules to the browser in the first place: external style sheets, embedded style blocks, and inline styles. The journey from your CSS file to the rendered pixel begins there. Section 1.9: 3 ways to insert CSS. You've written your first CSS rules. You know how a style sheet is structured and how elements are categorized. Now the question is, how do you actually deliver those rules to the browser? There are exactly 3 mechanisms. You can link to an external CSS file, you can embed a style block directly inside your HTML document, or you can apply styles inline on a specific element using the style attribute. All 3 methods work, and you'll encounter all 3 in the real world. But they differ dramatically in terms of maintainability, reusability, performance, and their position in the cascade. In this section, we'll survey all 3 at a high level so you understand when to use each and when to run far away. The first and most powerful method is the external style sheet. You write all your CSS in a separate file, usually with a .css extension, and you link to it from your HTML using a link tag in the document head. The browser fetches that file, parses the CSS, and applies it to the current page. The magic of this approach is that you can link the exact same CSS file to hundreds of pages across your website. Change the color in one place, and every page updates instantly. The HTML remains pristine. No style information pollutes the markup. And because the CSS file is a separate resource, the browser can cache it. When a user navigates from your home page to your About page, the CSS file doesn't need to be downloaded again. It's already there. This is the gold standard for CSS delivery, and it will be your primary method throughout this course. The second method is the internal style sheet, also called an embedded style sheet. You write your CSS directly inside the HTML file, wrapped in a style element, typically placed in the document head. This is convenient for quick experiments, single-page prototypes, or situations where you want to keep everything in one file. However, internal styles come with a significant trade-off. They cannot be shared across pages. If your site has 10 pages, and you use internal styles, you have to duplicate those CSS rules in every single HTML file. Make a color change? You're updating 10 files. Additionally, because the CSS is embedded in the HTML, it can't be cached separately. Every time the page loads, the entire HTML, including the CSS, must be downloaded fresh. In the Cascade, internal styles have the same origin and specificity as external style sheets. They compete purely by source order. So if both an external and an internal rule target the same element with the same specificity, the one that appears later in the document wins. This is why you often see internal styles used to override external styles temporarily during development. The third method is the inline style. You apply CSS directly to a single element by adding a style attribute to its HTML tag. The value of that attribute is a string of CSS declarations. No selectors needed, because the target is the element itself. Inline styles have the highest specificity of any normal author origin declaration. They will override any external or internal style sheet rule, even those using ID selectors, unless those other rules are marked with the important flag. This power sounds useful, but inline styles are a maintenance disaster at scale. They mix presentation directly into the markup, undoing the separation of concerns that CSS was invented to provide. Changing the design of your site means hunting through every HTML file to find and update style attributes. There are only two situations where inline styles are genuinely appropriate: when JavaScript needs to dynamically update an element's position or visibility in real time, and when writing HTML emails, because many email clients strip out style blocks and linked style sheets. For everything else, keep your styles out of your elements. So let's put it all together. External style sheets are the professional standard: reusable, cacheable, and maintainable. Internal style blocks are handy for quick experiments and single-page demos, but they don't scale. Inline styles are a last resort, justified only by dynamic JavaScript updates or the bizarre world of HTML email. The golden rule: always prefer the external style sheet. Keep your content and presentation separate. Your future self, your teammates, and your users will all benefit. In the upcoming sections, we'll explore each of these three mechanisms in meticulous detail, starting with the link tag and how to master every one of its attributes. We've now mapped the 3 routes CSS takes to reach the browser. Each has its purpose, its strengths, and its pitfalls. The rest of this chapter will take you on a deep dive through each one. You'll learn to use the link tag like a pro, when and why to embed styles directly, how the add import rule can silently hurt performance, how CSS files travel over the network, and how to wield inline styles responsibly when you absolutely must. This is the plumbing that makes styles appear on screen. Let's get into the details. Section 1.10. The external link, the link tag deep dive. The link tag is the primary and most powerful way to bring CSS into your HTML. It lives inside the document head, never in the body, and it establishes a relationship between the current page and an external resource. For CSS, that relationship is Stylesheet. The ref attribute points to the URL of your .css file, which can be a relative path like styles.css or an absolute URL. When the browser's HTML parser encounters a link tag with rel equals Stylesheet, it pauses, fetches that CSS file over the network, parses it, and then continues rendering the page with the styles applied. This fetch is render blocking by default, meaning the browser won't display anything until the CSS arrives, because an unstyled flash of content would be a terrible user experience. The link tag is the cornerstone of modern web architecture, and mastering its attributes is the key to controlling how and when your styles load. The link tag comes with several attributes that give you precise control over how style sheets behave. The rel attribute tells the browser what kind of resource this is. For CSS, it's always Stylesheet. The ref attribute provides the path, relative for files in your project, absolute for external CDNs. The type attribute, text/CSS, was required in older HTML versions but is now optional. The browser assumes CSS by default. The media attribute is incredibly powerful. By setting media equals print, you create a style sheet that only applies when the user prints the page. By setting a media query like media equals open parenthesis max width colon 600px close parenthesis, you can conditionally load styles based on viewport size. Though this still downloads the file, it only applies the rules when the query matches. The disabled attribute tells the browser to download but ignore the style sheet, useful for toggling themes with JavaScript. And the title attribute, when combined with rel equals alternate style sheet, creates a selectable alternate style that users can choose from their browser's menu. These aren't just historical quirks. They're the foundation of responsive and accessible design. A single page can link to multiple style sheets, and this is actually common practice. A typical project might have a reset.css to normalize browser defaults, a base.css for typography and common styles, a components.css for reusable UI pieces, and a theme.css for color and branding. The browser treats all these linked style sheets as part of the same author-origin cascade. That means source order matters enormously. If two linked files contain rules with identical specificity for the same element, the file that is linked later in the HTML wins. This is the Cascade's source order tiebreaker in action. So your theme file must come after your base file to override its defaults. You can think of the sequence of link tags as layers of a cake. The bottom layers provide the foundation, and the top layers add the final polish. This same principle applies to internal style blocks too. A style block that appears after a link tag in the HTML will have higher cascade priority than that linked file. By default, CSS linked with link rel equals style sheet is render blocking. The browser waits for it before showing any content. For your main style sheets, this is exactly what you want. No one likes a flash of unstyled content. But for performance-critical pages, you can use link rel equals preload to start fetching an important CSS file even earlier, before the browser would normally discover it. The as equals style attribute tells the browser what kind of resource it's fetching, so it can set the right priority and content security policy headers. Once the file loads, the onload handler changes the rel to style sheet, and the CSS is applied. On the other end of the spectrum, link rel equals prefetch tells the browser, I don't need this file right now, but I might need it on the next page, so download it quietly in the background. Prefetch is speculative, low priority, and perfect for style sheets you anticipate needing soon. Together, preload and prefetch give you fine-grained control over the loading sequence, reducing perceived load time and keeping users happy. Where should the link tag go? Always in the head, never in the body. Why? Because the browser needs the CSS as early as possible to avoid a flash of unstyled content and to correctly lay out the page. The optimal position is early in the head, after the charset declaration and the title, and before any synchronous JavaScript. JavaScript can also block rendering, and if your scripts rely on the CSS to compute element dimensions, you need the styles loaded first. A common pattern is preload critical CSS, then link to the main style sheet, then load any scripts. If you put the link tag in the body, the browser has already started rendering with default styles, and then has to reflow the page when the CSS arrives, wasting time and causing visual jank. Keep your link tags where they belong, high in the head, paving the way for a smooth, styled experience. The link tag is your primary gateway to CSS. The small, but its attributes give you immense power over how and when styles load. Use the media attribute for conditional styling, manage source order for cascade control, and leverage preload and prefetch for performance wins. Always place your link tags in the document head, high up, to ensure styles are ready before the first pixel appears. In the next section, we'll explore the style element, the second method for inserting CSS, and when embedding styles directly in your HTML is the right call. Section 1.11. Embedded styles, styling in the document head. The style element gives you a second way to insert CSS into a page. Instead of linking to an external file, you write your CSS directly inside the HTML document, wrapped in an opening style tag and a closing style tag. This is called an internal style sheet or an embedded style sheet. It's typically placed inside the head, though it can technically appear in the body as well. More on that later. When the browser's HTML parser encounters a style block, It stops building the DOM momentarily, parses the CSS inside, applies it to the current page, and then continues. The result is exactly the same as if those rules had been in an external file. The cascade, specificity, inheritance, everything works identically. The difference is purely in where the CSS lives. The trade-off between external and internal style sheets comes down to three things: reuse, caching, and convenience. With an external style sheet, you write your CSS once and link to it from every page. The browser downloads it once, caches it, and reuses it for subsequent page views. Change one line and every page reflects it. This is maintainable and performant. An internal style block, on the other hand, is confined to a single HTML file. That means no caching. The CSS must be downloaded again every time the user visits that page. If you have multiple pages, you have to duplicate the same CSS into each one. But the upside is immediacy. Everything lives in one file, which can be ideal for rapid prototyping, self-contained demos, or very simple one-page sites where an extra HTTP request isn't worth the overhead. The internal style sheet is a specialized tool, not a general-purpose replacement for the link tag. In the Cascade, internal style sheets are not special. They have the same origin, author, and the same specificity rules as external style sheets. The only tiebreaker is source order. Whichever set of rules appears later in the HTML document wins when everything else is equal. So if you have an external file like base.css linked first, and then a style block with overrides later in the head, the internal styles win. If you reverse the order, the external styles win. This makes internal style sheets very useful for page-specific tweaks. You load your global styles first, then drop in a small style block that overrides just a few things for this particular page. It's a lightweight way to customize without creating a whole new external file. But be careful. The same logic means that if you naively add a style block before your main style sheet, it will be overridden, and you'll wonder why your styles aren't working. Always pay attention to where your style block sits among your link tags. One of the most powerful modern uses for internal style blocks is delivering critical CSS. Critical CSS is the minimal set of styles needed to render the content that the user sees immediately, the area above the fold, before they scroll. By extracting those essential rules and placing them directly in a style block inside the head, you eliminate the network round trip for the CSS that matters first. The page can render instantly, while the full external style sheet loads in the background. This technique dramatically improves perceived performance, especially on slow connections. Without it, the user stares at a white screen until the entire CSS file arrives. With it, they see a styled page in milliseconds. The trade-off is that you have to maintain both the critical inline CSS and the full external file, but build tools can automate this extraction. The key takeaway: the style block is not just for prototyping. It's a performance optimization tool when used strategically. HTML once had an attribute called scoped, which you could add to a style element to limit its styles to the parent element and its children. It was a beautiful idea, true component-level scoping without any build tools. But it was never fully adopted, and it was removed from the HTML specification. Today, we are gaining a much more powerful spiritual successor, the CSS @scope rule. With the @scope rule, you can write a style block that declares a scoping root, like a class named card, and any rules inside that block only apply to elements within that root. This is native CSS scoping, no JavaScript required. It's still emerging, but it represents the future of internal and external styles alike. Styles that know where they belong. For now, remember that the old scoped attribute is dead and should never be used. If you need scoping today, you rely on naming conventions, CSS modules, or the Cascade itself. But keep an eye on the @scope rule. It will change how we think about embedded styles. The style element is your in-document CSS workhorse. It's not a substitute for external style sheets in production, but it's an indispensable tool for prototyping, performance optimization, and page-specific overrides. You now understand how it fits into the Cascade, where to place it, and when its use is justified. In the next section, we'll explore another way to bring CSS into a page, the @import directive, and why it can be a hidden performance trap if you're not careful. Section 1.12. Importing Stylesheets. The @import cascade. We've seen external stylesheets loaded via the link tag and internal stylesheets embedded directly in the HTML. But there's a third, more subtle mechanism, the @import directive. The @import rule allows one CSS file to load another CSS file. You write it inside a stylesheet, either an external .css file or an internal style block, and the browser fetches the imported file and merges its rules into the current stylesheet. At first glance, this seems like a powerful organizational tool. But @import carries significant performance and cascade implications that many developers overlook. Let's explore how it works, when to use it, and why it's often considered an anti-pattern. The syntax is straightforward. You write @import, followed by either a quoted URL string or the URL parentheses function, followed by a semicolon. Optionally, you can append a media query to conditionally load the imported file, just like the media attribute on a link tag. But there's a strict placement rule. All @import directives must appear at the very top of the style sheet, before any other rules, except possibly an @charset declaration. If you try to put an @import after a regular selector, the browser will simply ignore it. This rule exists because the cascade needs the full picture before it can resolve any styles. It's a syntax constraint that can easily trip you up if you're not paying attention. Here's the real problem with @import performance. When the browser encounters an @import inside a style sheet, it must first download and parse the containing style sheet, then discover the @import, then start downloading the imported file. This creates a sequential chain of network requests, a waterfall. The page cannot render until the very last file in that chain arrives. In contrast, when you use multiple link tags in your HTML head, the browser discovers all of them simultaneously and can fetch them in parallel over modern HTTP/2 connections. This makes the page appear much faster. For this reason, many developers flat out ban @import from production CSS. It's not that it doesn't work, it's that it works slowly. It's critical to distinguish between native CSS @import and the @import used in preprocessors like Sass or Less. In a preprocessor, @import is a compile time instruction. The tool reads the imported file and merges all the CSS together into a single output file before it ever reaches the browser. That's perfectly fine, it's a developer convenience. But the native CSS @import that runs in the browser is a runtime request, and it's subject to all the waterfall delays we just described. When you see CSS @import in the wild, it often comes from legacy code or from developers who migrated from Sass and didn't realize the difference. Know which one you're dealing with. Is @import completely dead? Not quite. In modern CSS, it has found a new purpose, combining with the @layer rule to load style sheets into specific cascade layers. By writing @import URL parentheses and then layer parentheses with a name like framework, you can place an entire imported style sheet into a named layer, ensuring it has lower priority than your custom styles, regardless of specificity. This is a legitimate use case because the cascade ordering is explicit and intentional. However, the performance waterfall still exists. For that reason, the best practice is to use @import with layers during development, but to use a build tool that resolves all @import statements and @layer declarations into a single, optimized file for production. The future may bring better handling, but for now, be aware of the trade-off. The @import rule is a powerful but dangerous tool. It can load style sheets conditionally, organize layers, and keep your CSS modular, but it does so at a performance cost that compounds quickly. For most projects, external link tags are the faster, more reliable choice. Understanding the difference between native CSS @import and preprocessor @import is essential to avoiding confusion. In the next section, we'll follow a CSS file on its journey from the server, across the network, through caching and compression, all the way to the user screen. Section 1.13. How CSS files travel across the internet. So far we've talked about how you write CSS and how you attach it to HTML. But between the moment you save your .css file and the moment it styles the page, something crucial happens. The file travels across the internet. It goes from a server, possibly on the other side of the world, through cables, routers, and data centers into the user's browser. This journey is fast, but it's not instantaneous. And how you manage that journey, caching, compression, delivery, directly affects how quickly your users see a styled page. In this section, we're going to follow a single CSS file on its network journey, and you'll learn every lever you can pull to make it lightning fast. It all starts with a request. When the browser encounters a link tag or an add import directive, it creates an HTTP request, specifically a GET request, asking the server for the file at that URL. The server responds with a status code, usually 200 OK, and includes the CSS file in the response body. But wrapped around that file are HTTP headers, metadata that tell the browser what to do with the content. The content type header says, "This is CSS." The cache control header tells the browser how long it can keep the file before asking again. The content encoding header reveals whether the file is compressed. These headers are the control surface for performance, and they're set by the server or the CDN. Every time a CSS file loads, this conversation happens. Optimizing it is the secret to fast pages. Caching is the single most powerful performance tool you have. When a CSS file is cached, the browser stores a copy locally. The next time the user visits any page that needs that file, the browser loads it from disk, no network request, no waiting. This is controlled by the cache control header. A long max age tells the browser to keep the file for months. But what happens when you need to update the CSS? The browser doesn't know you've changed the file unless the URL changes. That's why we use cache busting. Appending a query string like $v = 2, or even better, including a hash of the file contents in the file name itself, like styles.a3f for b2.css. When the content changes, the file name changes, and the browser fetches the new version. Caching with cache busting gives you both speed and control. CSS is text, and text compresses beautifully. Before sending the file over the network, the server can run it through a compression algorithm, either gzip or the more modern Brotli. This reduces the file size by 70 to 80% without losing a single character. The browser indicates it can accept compressed content with the accept encoding header, and the server responds with the content encoding header and the compressed bytes. The browser decompresses the file transparently before parsing it. This is not something you have to write any CSS for, it's a server configuration. But it is absolutely essential for performance. A large, uncompressed CSS file can take seconds to download on a slow connection. The same file compressed takes a fraction of that time. If you deploy a site without compression, you are wasting your user's time. Always make sure gzip or Brotli is enabled on your server or CDN. A single server can only be in one place. If your server is in Virginia, a user in Tokyo might wait an extra 200 milliseconds just for the signal to cross the ocean. A content delivery network, or CDN, solves this by distributing your files to a network of servers around the world called edge nodes. When a user requests your CSS file, the CDN routes the request to the nearest edge node, which already has a cached copy. The latency drops from intercontinental to regional. CDNs also handle compression, caching headers, and scaling automatically. Services like Cloudflare, Fastly, and Akamai make this trivial to set up. For any globally used website, a CDN is not optional, it's fundamental. You can see this entire journey play out in real time using the browser's DevTools network panel. Open it, reload your page, and you'll see a waterfall of every request. Find your CSS file, click on it, and inspect the headers. Is cache control set? Is content encoding present? How large is the file after decompression? You can even simulate slow connections to feel what your users on 3G networks experience. The network panel is the truth teller. It shows you exactly how long your CSS takes to load, whether it was cached or fetched, and whether compression is working. Developers who skip this step are flying blind. Spending 5 minutes in the network panel can reveal a 10-second problem that your users are silently suffering. The final piece of the delivery puzzle is the network protocol itself. Under the old HTTP/1.1, each request for a CSS file required a separate connection, and browsers limited the number of parallel connections. Developers responded by bundling all their CSS into a single massive file, because one big request was faster than many small ones. HTTP/2 changed the game. It allows multiple requests and responses to be multiplexed over a single connection, meaning the browser can fetch several CSS files in parallel without the old overhead. So, under HTTP/2, having multiple smaller, focused style sheets is no longer a performance sin. You can separate your reset, layout, components, and theme into individual files, and the browser will load them efficiently. That said, bundling is still valuable if you have many tiny files, because each request still has some overhead. The key is to understand your protocol, test your waterfall, and make deliberate choices, not follow outdated dogma. Your CSS travels a long way. It starts as a text file on a server, gets compressed and sent across the globe through a CDN, cached in the user's browser, and finally parsed and painted onto the screen. Every step of that journey is an opportunity for optimization. Enable compression. Set caching headers. Use a CDN. Inspect your network waterfall relentlessly. Understand the protocol your server uses. When you master the network journey of CSS, you deliver beautiful, fast experiences to every user on every connection. In the next and final section of this chapter, we'll cover the last method of inserting CSS, inline styles, and why they are the nuclear option. Section 1.14, Inline Styles, the nuclear option. We've explored external style sheets, the gold standard. We've covered internal style blocks, useful for prototyping and critical CSS. Now we arrive at the third and most dangerous method of inserting CSS, the inline style. An inline style lives inside a single HTML tag style attribute. You write CSS declarations directly as the value of that attribute, and those declarations apply exclusively to that element, no selector needed, because the target is right there. It's immediate, it's powerful, and it's almost always a bad idea at scale. Inline styles are the nuclear option. Devastatingly effective in the right circumstances, but radioactive if you spread them throughout your codebase. Inline styles carry the highest normal specificity in the Cascade. In the 4-part specificity scale, they occupy the first slot, 1, 0, 0, 0. That beats any combination of IDs, classes, and element selectors. If you write an inline style on an element, no external or internal rule can override it, unless that other rule uses the important flag. The important flag is the only thing with higher priority in the author origin. This is why inline styles feel unstoppable. They bypass your carefully crafted stylesheet architecture. But that power is a trap. When every element has its own inline styles, you lose the ability to make global changes. You're back to the pre-CSS nightmare of hunting through HTML files to change colors, fonts, and spacing one element at a time. The true cost of inline styles is maintenance. Imagine you have 100 buttons across 50 pages, each with its own inline styles. The designer decides the border radius should change from 4 pixels to 8 pixels. If those buttons used a shared CSS class, you'd change one line in a style sheet and be done. With inline styles, you must find every single button, every single instance of that attribute, and manually update each one. You will miss some. You will introduce inconsistencies. You will spend hours on a task that should take seconds. This is the exact problem CSS was invented to solve. Inline styles rip that solution apart and scatter it across your markup. They are the opposite of separation of concerns. There are exactly 2 scenarios where inline styles are genuinely appropriate. The first is JavaScript-driven dynamic styling. When you need to move a tooltip to follow the mouse cursor or animate an element's position in response to user input, you use JavaScript to set the element style property. This is per element, per frame, and essential for interactivity. It's not a replacement for style sheets. It's a runtime override for values that cannot be known ahead of time. The second scenario is HTML email. Email clients are notoriously hostile to standard web practices. Gmail strips style blocks. Outlook ignores linked style sheets. The only reliable way to style an email across all clients is to use inline styles on every element. This is a grim necessity, not a best practice. If you're building a website or a web application, Inline styles should be vanishingly rare. If you're building an email, they're your only option. So where do inline styles fit in your toolkit? At the very bottom of the preference list. External style sheets are your daily driver. Internal style blocks serve prototyping and critical CSS. Inline styles are a last resort. If you find yourself writing style equals double quote some rules double quote in your HTML for reasons other than dynamic JavaScript or email, stop and ask, could this be a CSS class? The answer is almost always yes. Respect the separation of concerns. Keep your content in HTML and your presentation in CSS. Use the Cascade to your advantage. The entire language is built to make your styles reusable, maintainable, and scalable. Inline styles throw all of that away for the illusion of convenience. Inline styles close the loop on our exploration of CSS delivery mechanisms. You now understand every way CSS can enter the browser. Through external files linked in the document head, embedded directly in style blocks, imported from within other style sheets, delivered over compressed, cached, CDN-accelerated networks, and applied inline as a last resort. You know the syntax, the performance trade-offs, and the maintenance implications of each method. Most importantly, you know why external style sheets are the foundation of everything we'll build from here. Chapter 1 is complete. In Chapter 2, we'll turn our attention to selectors, the mechanism by which CSS targets the DOM. You'll learn to aim your styles with surgical precision. Let's go.